In this lecture video, we will learn about elimination reactions, which are the types of reaction that are then used to make alkenes. Elimination reactions is basically when the reagent is performing a basic attack on the substrate or the electrophilic carbon on the substrate instead of the nucleophilic attack that is seen in substitution reaction, as below. So, given the structure of a substrate, what we have seen in substitution reaction is that when we do substitution reaction, the nucleophile come in to attack this carbon right here, the electrophilic carbon, or also called the alpha carbon. And these are the beta carbon, and this would then be the gamma carbon. So in substitution reaction, the nucleophile come in to attack the electrophilic carbon. And kicking up the leaving groups. So in the product, the nucleophile is replacing the leaving group. So this is what we have seen in substitution reaction. And in this case, the nucleophile is then said to do a nucleophilic attack. In elimination reaction, the reaction will be slightly different. And this is what happened. So in this case right here, when we react this with the reagent, rather than performing as a nucleophile, the reagent is now acting as a base and undergoing something that we call a basic attack, in which it does not attack the electrophilic carbon or the alpha carbon directly. Instead, it actually picks up the beta hydrogen or one of the hydrogen at the beta position. And once this electron is picked up as a base, as a proton, the electron is then donated in to form the double bond between the alpha and the beta carbon. And now the electron is then donated to the leaving group and breaking up the leaving group. And in the product, we will now form a double bond between the alpha and the beta carbon. So this will be the product of elimination reaction. And it basically is an alkene. Versus over here, this is the substitution product. And in this case, this reaction is called an elimination reaction. And again, elimination reaction refers to the reaction where the reagent is acting as a base and doing a basic attack on the electrophilic carbon. And some of the notes are as follows. So the proton abstraction happened at the beta atom. Basically, the hydrogen at the beta carbon is being removed. In this case, this would then be the beta hydrogen. Now, we can also have beta hydrogen over here on the other side as well. And if there are multiple beta hydrogen, or if there are different beta hydrogen, then different alkene may be formed. So we can pick up a beta hydrogen from this carbon or this position over here. Depending on the structure of the substrate, it may lead to different types of alkene that being produced. And the double bond only formed between the alpha and the beta atom or carbon. So therefore, we call this beta elimination. Substitute or elimination reaction can also be referred to as beta elimination reaction. So also called beta elimination reaction or 1,2 elimination. The reason why this is called 1,2 elimination is that the hydrogen is being removed on the first atom and the leaving group leave on the second atom, and now the double bond is formed between the first and the second atom. So therefore it called the 1,2 elimination as well. And as elimination reaction happen, it exhibit 2 of the 4 steps. And in this case right here, that these 2 steps right here are also referred to as the core steps. And those 2 steps as follow. First, the proton transfer. And the second core step that must happen in elimination is the loss of the leaving group. This is very much similar to SN1 and SN2 reaction that we have seen already. And in fact, an elimination reaction can occur through either an E2 or an E1 reaction mechanism. The E1 and the E2 mechanism are as follows. First one, the concerted mechanism is basically similar to the referred to as the E2 mechanism. This is when the base abstraction or the proton transfer at the beta proton and the leaving group happen simultaneously. Very similar to the SN2 reaction, where the 2 steps happen simultaneously. For an example, so let's say here we have our substrate with the leaving group. And now this would then be the beta position. Let's now draw one of the hydrogen on this beta carbon. So when we have a base, the base will then come in, pick up this proton. So this step right here is the proton transfer. Oops. Let's make correction for this error. And now follow by this electron donating in, and the leaving group it then breaks up. So this step right here is the loss of the leaving group. So the proton transfer and the loss of the leaving group happen simultaneously and now producing this product. So again, this is the alpha position and this is the beta position. So in this case, the double bond will be formed between the alpha and the beta position. And now the leaving group has broken up with the electron. And the base now has the proton on it. So this would be the E2 mechanism. And similar to the substitution reaction, the elimination can also happen in the stepwise manner, in which that the loss of the leaving step would happen first, followed by the basic attack on the beta proton. So in this example right here, this would be the mechanism. So this is the substrate. And now the first thing going to happen is the leaving group breaks off first. So the loss of the leaving group happen first. And what will then be producing will then be an intermediate. And this is a carbocation intermediate, followed by the base coming in to pick up one of this beta hydrogen. And now the electron is donated in to form the double bond between these 2 carbons, producing these products. So these are the 2 possible mechanisms, very much similar to substitution reaction. Now we have an E1 and an E2 mechanism. So the E2 mechanism is the concerted mechanism, where the stepwise mechanism is also called the E1 mechanism. Let's now discuss the E2 mechanism in great detail. So again, it is the concerted mechanism where the basic attack on the proton and the loss of the leaving group happen simultaneously. And much like the SN2 reaction, the rate of this E2 reaction is linearly dependent on the concentration of two compounds, the substrate and the base. So this is why that we call this an E2 reaction or biomolecular reaction. So the rate of the reaction is then equal to K multiplied by the concentration of the substrate multiplied by the concentration of the base. So the rate of the reaction is sensitive to the concentration of two substances, the substrate and the base. So therefore biomolecular. And therefore E2 reaction. And the energy diagram of an E2 reaction involves as follows. So in this case, using this as an example where hydroxide is serving as a base. And now this is our substrate. So in the transition state, then the base come in to pick up one of this hydrogen in here. And now breaking this bond, donating in here to form this double bond. And now the bond between the carbon and the leaving group. In this case, the leaving group is the bromine, is been broken. So in the transition state, we can see the bond between the hydroxy group and this hydrogen is forming. And now the bond between this beta carbon and this hydrogen is breaking. And now the bond between these two carbon, the double bond between this alpha and this beta carbon right here is forming in the transition state. And finally, the bond between this alpha carbon and the leaving group is breaking. And that is something we will see in the transition state. Now, please note that this reaction right here happened in one step. So there's no intermediate that is being formed, but only the transition state. And now, let's discuss the effect of the substrate on the E2 reaction mechanism. In the opposite trend, or unlike the SN2 reaction, the E2 reaction is favored by big and steric substrate. We have seen in substitution reaction that SN2 reaction would prefer a less steric substrate. However, in elimination reaction, a big and steric substrate is actually being favored in elimination reaction. And the reason why is as follows. In substitution reaction, our reagent or the nucleophile is coming in to attack this electrophilic carbon right here directly. And therefore, the more bulky the substrate, the more difficult for the nucleophile to come in to attack. So this is why it would then favor a smaller substrate. However, in elimination reaction, the hydroxide here is serving as a base. And being a base, all it have to do is pick up a proton. It does not even attack this carbon right here directly, but it actually pick up the proton at this beta position. And therefore, it is much less steric. And therefore, it can come in and pick this up easily. So steric is not a problem at all. And this is why that the bigger the substrate, then the faster the rate of the reaction. So we have observed that the tertiary substrate react more rapidly in E2 reaction compared to the less steric substrate. So in this case right here, the rate of reaction is increasing in this direction. So this is increasing rate of the reaction. This will be fastest, and this would then be the slowest. And the explanation for this is as follows. When we compare the transition state in an E2 reaction between a primary substrate, a secondary substrate, and a tertiary substrate, if we were to have a tertiary substrate, then the transition state is actually more stable. And because it is more stable, it actually is lower energy or have a smaller activation energy compared to the primary or the secondary substrate. So in this case, the transition state is more stable when we have a more bulky substrate, and therefore have a smaller activation energy and therefore faster reaction rate. The reason why that the tertiary substrate have a more stable transition state is then as follows. If we were to go back and review the previous energy diagram, here's what happened in the transition state, and the differences between the different substrate would be the amount of substitution on this carbon. So in this case right here, we would then see this carbon, this alpha carbon is actually carrying a positive charge in the transition state, and therefore the more bulky or the more substitution that this alpha carbon has, the more of it that it has, then it can donate electron to stabilize the positive charge on this carbon in the transition state, and thus stabilize the whole structure of this entire molecule, making this transition state structure have lower energy and therefore easier to react. So that is the explanation. And again, it has to do with the stability of the transition state. The more substitution that exists on this alpha carbon, the more stable this structure would be. So this alkyl group are electron donating group that will donate electron to stabilize this positive charge on the alpha carbon. So that is the explanation why the tertiary substrate would undergo elimination reaction faster than the less substituted substrate. Let's now focus on the regioselectivities of E2 reaction. In elimination reaction, multiple products can be produced if there are different beta hydrogen. And this is where we will discuss the Seychelles rule. So this is called Seychelles rule. Seychelles rule states as follows. A more substituted alkene would be favored in case that multiple alkene can be produced. The more substituted the alkene, then the more likely it would be formed, or the more it is in favor. And the more stable alkene is then called the Seychelles product. For an example, if we were to have this substrate right here, perform an elimination, an E2 reaction on this, since there are different beta carbon, and this beta carbon have beta hydrogen on them, the base can come in to pick up this hydrogen, which then produce the double bond between these two carbon. Or the base can also come in and pick up this beta hydrogen over here, producing the double bond between this alpha and this beta carbon. So therefore, these are the two products that would be possible. The product above, this is a more substituted alkene. And we have learned already that the more substituted the alkene, the more stable it is. And this product would then be called the Seychelles products. The product on the bottom, this is where we form an alkene on the end of it. So this alkene right here is then said to be less substituted. And this product right here is called the Hofmann product. Because both products may be possible in elimination reaction, ideally speaking, the Seychelles product is the more favored product over the Hofmann product. However, if by choosing the appropriate base, we can favor both either one of this product in here. So basically, the regiochemical outcome of each reaction can be controlled by carefully choosing the base. Please change this to regiochemical outcome. So again, regio refers to the region where chemical reaction is taking place. If we were to use a small base has been found to favor the Seychelles product. Whereas if we were to use a big and bulky base, that will then favor the Hofmann product. And below are some of the data. So in this case right here, going back to the same substrate that we have seen above, and this will be the Sage's product, and this is the Hofmann product. If we were to be using varying the base, in this case right here, this ethoxide, then the yields of these two products would then be as follows: 70% the Sage product and 29% the Hofmann product. And again, we see in this case that this is the more stable product, so therefore it gets formed more. However, if we were to now change it to a different base, in this case right here, the terbutoxide, then we will observe the following yield: 28% of the Sage's product and 72% of the Hofmann product. So in this case right here, we will then see the yield of the Hofmann product is increasing significantly. And if we were to now try this, change it to an even more bulky product, then the yields of the Hofmann product increase even more, and the yields of the Sage's product is then reduced significantly. And the reason is then as follows: the more bulky the product, then it would then prefer to pick up the hydrogen, the beta hydrogen on the outside, and therefore favor the production of the less substituted alkene. Whereas if we will have to have a small base has no problem coming in, pick up the proton either from this hydrogen or this hydrogen. So we have no problem either pick up this one or this one. But it would prefer to pick up this hydrogen right here, so that way it can produce the more stable product or the Sage's product. In the end, the more stable product is in favor when there's no selectivity between these two different beta hydrogen. But if we were to use a big and bulky base, this is where it becomes more difficult for the base to come in to pick up this hydrogen right here due to steric. So we'd rather pick up the base on the terminal end, so that way we'll be able to produce the less substituted alkene or the Hofmann product. And some of the common big and bulky base as follow. So this is called terbutoxide, and some of the other bigger base is also called diisopropylamine or triethylamine, and these are the chemical structure. So basically, the more bulky this alkyl group in here, then the more bulky it's become. And now let's try some practice problem. Predict the major and the minor product of this following elimination reaction. So in this case right here in A, we have this substrate reacting with sodium methoxide. Now sodium methoxide, this is a base, and it is small, not bulky. It is strong base, and it's not bulky. So here in this case right here, the major product will then be the Sage's product, where it will pick up this hydrogen here to produce a more substituted alkene. So the base will come in, pick this up, come here, donate electron in to form the double bond between these two carbon, and now kick off the leaving group. So in this case, the major product will then be the products where we have this alkene right here. And the minor product would then be the Hofmann product. So this would then be the Sage's product. The Hofmann product is when the base come in and pick up this beta hydrogen over here. So again, these are the beta position. And in this case right here, the base can also come in and pick up this hydrogen in here. And now we'll be producing this other product in here, where the double bond is from above here. So in this case, when the base come in to pick either this hydrogen from this beta carbon or this from this beta carbon, we will produce the same products. But when they pick up this hydrogen from this beta carbon, then we would then be able to form the other product. So this would then be the major product, and this would then be the minor product. And this product is called the Hofmann product. And now moving on to the example B. Here in this case right here, we are taking this substrate and reacting this with third butoxide. And third butoxide is a big and bulky base. So in this example right here, this is the alpha carbon and these are the beta position. And we can see the beta position is quite steric, so therefore it's more difficult for a big and bulky base to come in and pick up the hydrogen in here. It'd be better for it to come in and pick up the hydrogen on this beta carbon from above. So therefore it will come in, pick up this base, put the electron in, and now kick off that leaving group. So in this case right here, the major product will be the product where we form this alkene. And the minor product, so this would be the major product. And in this case right here, this major product right here is the Hofmann product. Whereas the minor products is when the base can come in to pick up the other beta hydrogen to produce the more stable alkene. So that would be the other product, or the double bond can form in here or on the other side. They would be symmetrical. So in this case right here, this would then be the minor product. And this is basically the Saychess product. So this is an example where the more stable alkene is actually the minor product. And again, it is because of the base. And in this example from above, in this example C, then we are taking this substrate and we are now reacting this with sodium butoxide. So what will be the products? So here in this case right here, so again this is our alpha position and this will be our beta position and this is then our beta position as well. So what would then be the product of this reaction? So the base can come in to either pick up this hydrogen or this hydrogen in here. And now the double bond will form between this alpha and beta carbon or between this alpha and this beta position. Let's draw both of the products. And now in this case right here, so let's draw the two products first before we determine which product would then be major and which one would then be minor. So this would be one product and the other products. And this would then be the other products. Between these two products right here, which one would be the major products? So here in this case right here, we would then again see that this is a big and bulky base. So therefore, it will then pick up the less steric beta hydrogen. And in this case, this hydrogen right here will be less steric. So therefore, this would then be the favored products. So this would then be the major product, and this will be a minor product. And in this case right here, between these two alkene, this major product of the alkene above here, this is actually is a more stable alkene compared to the alkene on the bottom. And the reason why is that this double bond right here is right next to a benzene, or it can say to be conjugated with a benzene, and it can come here to form resonance. So this is actually the more stable products. And in this case right here, this is both the more stable products and this is actually the Saychess product as well. So this is the more stable product and this is also the Saychess product, since this is more stable. And on D, when we taken this substrate reacting with sodium hydroxide, what would be the major product? So here in this case right here, sodium hydroxide is a small base. So we have no problem picking up the internal hydrogen So in this case, this is our alpha carbon, and this is our beta. This will be our beta hydrogen. So we can see here in this case right here, both the beta hydrogen are equally steric because they're both secondary. And now in this case right here, we can have the base come in to pick up this base to now form the double bond between this alpha and this beta position. So the one of the product that is possible will then be this product, with the double bond is formed between these two carbon. And the other products will then when the double bond is formed between these two carbon in here. And that would be this product right here. So between these two products right here, which one would then be major? And the answer, this would be the major product right here, since this is the more stable alkene. So, and the reason why, because these two alkene right here are then said to be conjugated. The electron can move back and forth between these two alkene to form resonance. Versus in here, the electron cannot move between these two double bonds. So therefore, this is the more stable products, and that would then be the major products. And now, let's focus on the stereoselectivity of E2 reaction. Very similar to the SN2 reaction, E2 reaction is stereoselective. The reaction would only proceed to produce certain stereochemical outcome, and it needs to meet certain requirements in order for the reaction to occur. So we will be able to produce certain types of selectivity or stereochemistry in the alkene, but not all types of alkene or stereochemical outcome would be produced. In E2 reaction, it then proceeds through something that we call the anti-coplanar or anti-periplanar approach. And the anti-coplanar and the anti-periplanar mean the following. The halide or the Levin group and the proton to be abstract on the beta hydrogen must be in anti-coplanar, or basically 180 degrees from each other in order for elimination to occur. And what this means is as follows. So here in the Newman projection, we will then see the following. So here is the X or the Levin group on the front carbon, and on the back carbon, so this is on the back carbon, and on the front carbon, this hydrogen right here and this X right here has to be 180 degrees from each other in order for elimination to reaction to happen. And the reason why as follows. If we were to actually view in here, it will help us see that the orbital will be overlapping in order for this reaction here to occur. So here in this case right here is the bond between the carbon and the Levin group, and the bond between the beta hydrogen and the beta carbon in here. So the base will come in and pick this up, and this will then donate the electron into the anti-bonding orbital from this CX bond. So these two groups right here, this hydrogen and this Levin group, have to be opposite to each other, or 180 degrees from each other. And the reason why is because of this anti-bonding orbital that is in here. So this is the anti-bonding orbital of this CX bond. And that is the location of the anti-bonding orbital. When the base comes in to pick up this hydrogen, this electron comes very close to this anti-bonding orbital, which it can begin to donate electron into this anti-bonding orbital. And an electron are donated into this anti-bonding orbital. The electron from this CX bonding orbital right here will become weaker and weaker, and therefore break up this CX bond right here. And now the electron, the bond can break up, and the electron can go to the Levin group. So this approach right here is called the anti-coplanar or anti-periplanar approach. If we were to have the CH bond and the CX bond, they're not 180 degrees from each other. In this case right here, have they been 0 degree from each other or any other degree, they deviate from 180 degrees. then what we will then see is that the orbital do not overlap well. So here in this case right here, first the repulsion in here would occur, and second, as the base come in here, the electron would not be able to donate into this anti-bonding orbital right here, but it will be because this is now parallel to this other orbital, to this bonding orbital in here. So it need to be donated into this anti-bonding orbital in order to weaken this CX bond for this bond to break up. But here in this case right here, if these two groups were to be together and their bond angle is 0 degree from each other, then now we can see they are not in the right orientation to donate the electron into the anti-bonding orbital. And therefore, there will be no reaction. So therefore, to basically be able to predict the stereochemical outcome of an E2 reaction, we have to rotate the carbon-carbon bond first to obtain the anti-periplanar approach. And this basically means that the hydrogen on the beta carbon and the leaving group has to be 180 degrees from each other, or anti-periplanar to each other, in order for the reaction to occur. And then the product and the stereochemical outcome would then proceed dependent on that orientation. So here's an example right here. So let's say here in this case right here, this is where we have these two bonds right here are opposite to each other. So here in this case, there's a point in here and there's a point up. Their bond angle is 180 degrees from each other. So this is called the anti-periplanar approach. And now let's go over in a few examples. So again, make sure we rotate on this carbon and carbon bond until this hydrogen and this bromine are opposite to each other. So in this case, they are now opposite. Once they're opposite already, the base would now be able to come in, pick up this, and now donate the electron in here and kick up the bromine. And now, in this case right here, once we adopt this anti-periplanar approach already, we would then observe that this R1 and this R1 right here, they are both wedge bond. So they are together, they close together. So as we produce the product, this R1 on this carbon and the R2 on the other carbon will be on the same side of the double bond. So the R1 and the R1 will be on the same side of the double bond. And now this R2 dash and this R2 dash, so now they be on the same side of the double bond as well. So that is what happened. Now another way for us to actually view this is to look at the Newman projection. When we draw the Newman projection, this is the structure of this molecule. So if we were to view from here, our front carbon would have the hydrogen pointing down. And now the R1 would then be on the right side, and the R2 be on the left side. So that would then be the front carbon. And now on the back carbon, then we will see the bromine is pointed up. It has to be opposite to this hydrogen right here, or 180 degrees from each other. And now the R1 is on the right side, and the R2 is then on the left side. So once we draw the Newman projection already, the double bond will then form between these two carbon in here. And now, if the two group over here will be on the same side when the double bond is formed, and the two group over here will be on the same side when the double bond is formed. So that means the two R1 group will be on the same side of the double bond as what being seen here. And the two R2 group will be on the same side of the double bond as well. And now let's try a different scenario. So here in this case again, so a different example. And now first we have to make sure we rotate this carbon-carbon bond here to obtain the anti-periplanar approach first. And that is when this hydrogen and this bromine are anti to each other. And here in this case right here, the double bond will be formed between these two carbon. And now this R1 here and the R2 here, both of this bond right here are wedge bond, meaning on the same side. So as we form the double bond, the R1 and the R2 would then be on the same side. And this R2 and this R1 would then be on the same side. So now the R2 here and the R1 here will be on the same side. So that will be the stereochemical outcome of these products. And again, we can also use the Newman projection to help us see this as well. So let's view from here. When we view from here, this will be the front carbon. On the front carbon, we have a hydrogen pointing down. And now the R1 group is on the right side, and the R2 group is then on the left side. As for the back carbon, on this back carbon, the bromine is now pointing up. And again, it has to be opposite to this hydrogen right here. And now the R2 group here is on this right side, and the R1 is then on the left side. And again, as the chemical reaction is happening, the double bond is formed between these two carbon. And now in this case right here, we will then see this R1 and R2 are on the same side, and this R1 and this R2 are on the same side. So therefore, that agree with what the product that we have seen here. So there are two ways for us to view this. We can use the dash and the wedge bond and rotate to make sure we put the leaving group and the hydrogen in the anti-periplanar approach first. Or we can use the Newman projection and make sure we rotate to have this leaving group and this hydrogen on the beta carbon be opposite to each other first. And this stereoselectivity of an E2 reaction would only be relevant if the beta position have only one proton. If there are multiple protons on the beta carbon, then both of those hydrogen may be removed, and therefore will form a mixture of different products. For an example, here in this case right here, so this is our beta carbon, and there are two hydrogen on it. Both of this hydrogen right here can be removed in the elimination reaction. There are two beta hydrogens. So the base can come in to either pick up this one, and now when it pick up this product right here, we will then see the product that we will be making is when we have this R1 and the R2 will be on the same side. And now there will be another hydrogen here, and the R3 will be down here. So that will be one of the product. The other product is what happened when this group right here, this hydrogen now rotated down. So we will rotate this bond down, and now the structure of it would be as follows. So we're going to keep everything in this carbon right here the same thing. And now let's call this the hydrogen A and hydrogen B. So in this case right here, we can actually rotate this to now make this hydrogen A pointing in this direction. Because yes, due to the rotation on this carbon-carbon bond, both of this hydrogen right here can take the position of the anti-periplanar orientation. So in this case right here, when we pull this down, then now the hydrogen A will be down here. And as that happens, then now the hydrogen will then be pointed up in here. That the hydrogen B will be up here, and then the R1 group will then be on the back. And as the elimination happens, then now we will then see that this HB and the R2 will then be on the same side. And now the R1 and the R3 are now on the same side. So both of this product right here can get formed. And now, let's discuss the E2 reaction whenever we have cyclohexane as our substrate. So for cyclohexane to undergo the E2 reaction, the ring must flip to have the leaving group at the axial position in order for it to take place. And the reason why that the anti-coplanar conformation can only be achieved when the hydrogen and the halogen or the leaving group occupy the two axial position right next to each other. So that would then mean that not all of the conformation of the cyclohexane will be suitable to undergo E2 reaction, but the ring must flip in order to put the hydrogens and the leaving groups to be in the axial position first, in order to undergo elimination reaction. For an example, when we take this bromocyclohexane and take it and react this with sodium hydroxide, we can actually produce this product in here. But if we were to analyze this product even further, then this is what happened. When we draw the structure of the bromine, so let's say here in this case right here, in this conformation right here, then right now this bromine and this hydrogen right here, they are both at the equatorial position, which cannot undergo elimination reaction. But now the ring must flip, and when the ring is flipped, now we have this bromine chain from the equatorial location into the axial location. And now the base can now come in and pick up this green hydrogen right here, because this hydrogen and this bromine are now anti-coplanar to each other. And again, the anti-bonding orbital of this carbon-bromine bond is down here. And as it pick up this electron, now this electron can be donated into this anti-bonding orbital, break up this bond, and now we have our eliminated products. And another way to also view this cyclohexane is by drawing the Newman projection. So in this Newman projection right here, again, this axial bromine and this axial hydrogen right here are 180 degrees from each other, and the double bond will be produced in here. Now, if we were to now have different types of cyclohexane with different substitution and alkyl group attached to it, this is where this reaction becomes quite important, and we must perform conformational analysis of the cyclohexane and flip to make sure that again the leaving group need to be pointing in the axial location, and only the hydrogen that is on the axial carbon right next to it will be able to remove and undergo the E2 reaction mechanism. Here is an example right here. So consider this following observation. Explain why some product get formed and some product did not get formed. So here in this case right here, we have this cyclohexane, and here is our leaving group. And we taken this and reacted this with a strong base, which is in perfect condition to undergo the E2 reaction. However, so you can see this is our alpha carbon, this is our beta carbon, and this is our beta carbon. Now, we do not observe the product where the double bond is formed between this beta carbon and this alpha carbon. We do not observe that product. So in here, this product right here is not observed. And we also do not observe the product where the double bond is formed between this beta and this alpha carbon by removal of this hydrogen. We do not observe that either. But we observe the product as follows. The hydrogen, or actually not the hydrogen, but the deuterium, so this D right here, it is the heavier isotope of hydrogen. It's very much similar to hydrogen, but a different isotope of hydrogen. So this is how we would label this. So in this case right here, only this deuterium, and again, very similar to the hydrogen, that get removed, and now we form the products between this beta carbon and this alpha carbon. So on the product, we observe the deuterium being removed, but not the hydrogen removed, because this hydrogen is still in here. We do not observe the product where this hydrogen is being removed, but only the product where this deuterium is being removed. So please explain why. And this would be good for us to start looking at our conformation and analysis. So here in this case right here, we have to draw the structure of the cyclohexane first. So here in this case, let's now draw the structure of this cyclohexane. And here in this case right here, so let's make this carbon right here, this carbon right here, our this carbon, and that would then be the leaving group. And here in this case right here, so we can see the hydrogen is now pointing up. That would be that hydrogen, and now the deuterium is pointing down. And on the following carbon, the methyl group is now pointing down. So in this case, right here, it is pointing down on this, and that would be the methyl group. So that is the conformation of this cyclohexane. And only in this conformation right here that it will undergo the elimination reaction. And in this case right here, we will then see that this bromine and this deuterium are anti-coplanar to each other. So the base will then come in, pick up this deuterium, the electron is donated in, and kick off the bromine leaving group. And now this is the reason why that we are now producing this product. And now let's try some additional practice problem. Predict the product of this following reaction. So when we take the substrate and we react this with sodium ethoxide, what would be the products? In this case right here, there will be no reaction. Why no reaction? The reason why is as follows. In this case right here, the leaving group is now pointing up. And now the hydrogen in this case right here is pointed up on this beta carbon, and the hydrogen is pointed up here in this beta hydrogen as well. So we will then see that it does not matter how we flip this cyclohexane. The hydrogen and the leaving group of the chlorine would always be on the same side. We will never be able to flip this to make sure that they are anti-coplanar to each other, and therefore no elimination. For an example, so let's say here we draw the conformation of cyclohexane. So in this case right here, let's make this our chlorine. And now the chlorine point up here, and the methyl group would be point here on one carbon and on the other carbon over here. So in this case, this hydrogen right here are both point up. So that is this conformation. And now we know in this conformation right here that it will not be suitable to undergo elimination reaction, because we are able to get our leaving group to be on the axial location. However, our hydrogen is on the equatorial position, and therefore no elimination reaction. If we were to flip this ring right here, we will then obtain the following. And now in this case right here, once we flip this, the chlorine become over here, and now the methyl group and the hydrogen on the other two groups. If we were to flip to put the hydrogen on the axial location, then now the leaving group become the equatorial location. So therefore we cannot get the anti-coplanar hydrogen to the leaving group. So no anti-coplanar. To the leaving group, and therefore no elimination, no E2 reaction. And now let's try another one. Let's try B. So please put in this. Let's make that a cyclohexane. So in this case right here, would we expect to have an E2 reaction? And the answer would then be yes. Now in this case right here, if we want to be able to draw the product quickly without doing conformation analysis, that would also be possible as well. And again, here in this case right here, in order to undergo elimination reaction on this beta carbon in here, there have to be a hydrogen that is now pointed on the opposite direction. In this case, on this first carbon, the hydrogen is now pointing up. So therefore, that basically means that we will not be able to undergo elimination by removing this hydrogen right here, because this hydrogen and this chlorine are on the same side. They are not anti-coplanar to each other. However, we can actually remove the proton from the other beta hydrogen, because on the other beta hydrogen, there's one hydrogen they point up and the other hydrogen they point down. It is now this hydrogen right here, the pointing down, that may be removed to undergo E2 reaction. And in fact, the base will come in, pick up that hydrogen right here that is pointing in the back, so that it can donate electron in, and now producing our products. And now this methyl group, it continue pointing back, and this hydrogen right here, it continue to point up. The stereochemical outcome of this product has not, on this carbon, has not been changed. But in this case, we are forming the double bond in here. So this would be a quick way for us to predict what will be the stereochemical outcome without drawing out the conformational analysis of the cyclohexane. And now, let's try some practice problem involving E2 reaction. So predict the major and the minor products for this reaction. So the stereoselectivity if relevant. So here in A, when we take this substrate right here, reacting with sodium ethoxide, will there be a reaction? And if yes, let's draw them. And again, show the stereoselectivity if relevant. So in this case right here, this is a strong base, which would then be ideal to undergo elimination reaction. And here in this case right here, we also have a secondary substrate. And we know the second substrate can undergo E2 reaction as well. It will not be as ideal compared to tertiary. However, it can still undergo E2 reaction. And in this case right here, we will then see that in this beta carbon, there's no hydrogen here. So therefore, the alkene would not be able to form between these two carbon. But now on this carbon, this all the beta carbon over here, there are now two hydrogen in it, one dash and one square. So here in this case right here, both of this hydrogen right here can be rotated to be in the anti-coplanar to this chlorine. So therefore, both of them can be removed to undergo elimination reaction. And again, whenever we have two beta hydrogen that can be removed, we will form a mixture of two different products having the different stereoselectivity or stereochemical outcome. So one of the product will be possible would then be this product right here, with a double bond it formed between that. And in this case right here, we would then have ourselves, this would then be an E stereochemistry. And the other product that will be possible would then be as follows. So in this problem right here, this product right here will be the product when this hydrogen right here is being removed. And let's call this the hydrogen A. So when hydrogen A is being removed, then we'll be forming the double bond across, and this two group right here will then be on the opposite ends of the double bond, and that will be that product. However, this molecule can also rotate to now put this hydrogen in the back, and that is when this ethyl group will be now point up, and that would then be the other product right here. Because the removal of both this hydrogen right here are possible, therefore we form both of this product. But between these two products right here, this would then be the major product, and this is a minor product, and it mainly because of different stability. This is the most stable product. And in elimination reaction, the more stable product is in favor. And now let's try B. So will there be a reaction? And the answer would then be yes. Right now, again, on this beta carbon, there's no hydrogen. But on this beta carbon over here, there's a hydrogen in here. And right now, this hydrogen and this chlorine is not in the correct orientation to undergo an elimination reaction. But first, we have to rotate this to put this hydrogen and this chlorine on the opposite of each other, or anti-coplanar to each other first, before elimination can take place. And here in this case right here, to approach this problem, because we have to do the rotation first, and that's where the Newman projection may come in handy. So now let's put in this hydrogen in here. There's a hydrogen here, point in the back. When we draw the Newman projection of this molecule, then this would then be as follows. On the front carbon, we have this group, this third butyl group, and now on the right side we have our chlorine, and now on the left side we have our hydrogen. So that would then be the front carbon when we view from this direction. And now for the carbon on the back, in this case right here, the ethyl group is now pointing down, and now the hydrogen would then be pointed on the right side, and the ethyl group is pointed on the left side, or the methyl group is on the left side. So that will be the orientation that we have right now. And right now we know that this is not the correct orientation for us to undergo elimination reaction, because this chlorine and this hydrogen right here, so the chlorine on the front carbon and the hydrogen on the back carbon, has to be anti-coplanar to each other. And how we'll be able to do that is by now taking this hydrogen right here on the back and rotate this over 120 degrees. So in this case right here, once we have the rotation already, so again, let's keep the front carbon the same thing. And now when we rotate this back carbon, we want to put this hydrogen right here. By rotating the back carbon 120 degrees. Then now the methyl group will then be down here, and the ethyl group will then be up here. But now we will then have the anti-coplanar approach. So this is now ready in the correct position to undergo the elimination reaction. And when that happens, the double bond will be formed between the front carbon and the back carbon. And now we will then see the two hydrogen will be on the same side of the double bond. And this third butyl group and the ethyl group will be on the same side of the double bond as well. So therefore, on our product, we will then see the following. The double bond, and now the ethyl group and the third butyl group will then be on the same side. So that will then be the stereochemical outcome of the products. Oops, this is actually a methyl group, not the hydrogen. So this methyl group. So the correct products is when this methyl group is right here and the hydrogen is right here. And again, a little bit more difficult to see, but we will see that the ethyl group and the methyl group are connecting to the same carbon. So in this case, this ethyl and this methyl need to be connecting to this carbon. So that's how we'll be able to draw the product of this reaction.